Hello, in this presentation I will be sharing with you the research topic Preprocessing Techniques for RNN-based Conversational AI that I, Hussein Mazyad, under the supervision of Dr. Joe Te'li and in collaboration with Julian Lammouz and Mr. Boulos Al-Asmar, have been working on for the past year and a half. The outline. This will be our outline for today. We will be discovering the motivation, receive an introduction, we will formulate the problem, we will set the goals and discuss the literature view as well as explore the approaches and understand the experimentation and view the results. The motivation. We all heard of at least one of these programs: Siri, Amazon Alexa, Google Assistant, or Cortana. Some people call them chatbots or personal assistants. The technical name, however, is Spoken Dialogue System Interfaces. It is a black box that when I input a sequence of text, it replies back with a meaningful sequence of text. So, what is inside this black box that gives me the answers I'm looking for? There are three main components of the dialogue system. It decodes the text to extract semantic information. It means that I retrieve the words that are meaningful and disregard the ones that are not. I know these words are meaningful, but I do not know yet what their meaning is. So here comes step 2. I process the semantic representation, and the processing is handled by the dialogue state tracker. This dialogue state tracker is called the DST. The DST, after processing, decides on what action to be performed. Some actions could be proposing a list of restaurants, or showing the directions to a location, or calling a contact. Each of these actions correspond to a specific domain. Proposing a list of restaurants, for example, falls in the restaurant reservation domain. Opening an app falls in the phone features domain. And last year, Anghami made it possible to interface with Siri. So we can deduce here that each of these domains requires a specific set of actions and rules. And for each possible domain in the realm of domains, the system will depend on the handcrafted rules. So my domains are restricted. This is the issue. It's too much legwork. In a nutshell, the motivation is to implement a spoken dialogue system that can understand anything without having to specify the rules, just like a human being. Now, the introduction. So, how did the dialogue state systems come into being? Well, we have witnessed major advances in the end-to-end training of neural networks, and at the same time, we have access to large-scale datasets. So we know what to train and how to train. The combination of these two powerful tools allow us to infer the dialogue policy from the conversational data, which means, in other words, that the system is able to figure out what the user wants just from the training of datasets received. And the backbone of these advancements is the use of the RNNs, the recurrent neural networks, which have been adapted to dialogue systems through encoder-decoder architectures. We will discuss more about these architectures in the literature review. On one hand, the RNNs have reduced feature engineering, so I do not need to do much manual work, but on the other hand, they require a lot of data, so it is purely data-driven. In order to work, we want to use RNNs, so it's aligned with the data-driven dialogue development. But to mitigate the issue of purely driven learning, we will be integrating external knowledge to regulate the output rather than being merely depending on the quality of the training data. The problem formulation. So, how do we proceed? Let us discuss first the implementation of the dialogue system. First, we pre-process the data set used as training data. And then we build and train the neural network. Then we test the obtained model, we pre-process the external knowledge base, then we add that to the training data, and then we retrain again. And at the end, we compare the results. But this is just one way of doing things. And we observed a few issues in this implementation. One, pre-processing techniques for end-to-end trainable RNNs-based conversational AI lacked common ground, which is the input and context representation. Two, pre-processing. The pre-processing techniques for additional knowledge lacked common ground, and little effort has been made to integrate knowledge at training time. So we can see here that the integration of external knowledge is still a new area, and every scientist or researcher approaches the problem in the way that they see fit. And so did we. We spotted an undiscovered area. That area is integrating the knowledge at the pre-processing step. So, what are the goals? While we are discovering this new area, we need to have a clear goal. That is, to reduce the dependency on the quality and quantity of training data, because most existing solutions to the authors rely solely on the quality of the training data to improve conversational quality. The second goal is to evaluate the impact of the external knowledge on the dialogue system. Will it be advantageous to incorporate a knowledge base or not? Now, the literature review. Going back to the technical aspect, how exactly do we use RNNs to train our models? We need to encode the words to numbers that the system can easily work with. So this is where the encoder comes into play. When the user enters a text or a sequence of words, the encoder will encode the sequence to a vector and feed it to the decoder. The decoder will do the processing and generates a sequence of its own that represents the output. Both the parts are practically two different neural models combined into one giant network. Now, the sequence-to-sequence model has been widely used for machine learning translation problems, like from English language to French language, but have recently shown promising results in mapping complicated structures, which has direct applications in natural language understanding. One of these applications is in dialogue response generation by mapping between queries and response, which is used in many recent works where RNNs have been used to model dialogue in short conversations. The nice thing about sequence-to-sequence models is that it requires little feature engineering and domain specificity, while surpassing state-of-the-art results. However, these models, being based on the current neural networks, suffer from vanishing gradient problem, which is not uncommon. That's why the variants of long short-term memory LSTM RNNs are mostly used. Another drawback is that it is often very hard to control the output of such models because it's primarily determined by statistical co-occurrences in the used training data, which results in incoherent responses. Now, the data we use in our experiments are from a restaurant reservation system dataset. These dialogues are derived from a real-world system, rendering the data as raw and real as we would hope for, while training a task-oriented dialogue system. The data is also linked to an underlying knowledge base of entities and their attributes, which we did exploit in this paper. So, what are the approaches? Well, we have followed three approaches in this experiment. First one is a knowledge-based integration. The KBI stands for knowledge-based integration, which is a representation of a user input and a system response, U1, S1. So this is a pair. For each response, there is a pair. Here, U and S represent the user and system requests and responses respectively, and K denotes the number of turns in the dialogue. We also have the all predicates KBI, and this means we are integrating the knowledge base in this scenario, where we check for predicates that occur in the knowledge base and intersect in the user input. And the intersecting predicates KBI is another variation of the all predicates KBI, but it is more enhanced. And we will discover how these three approaches are different in the next slides. Also, in each of these approaches, we have included history variations of 0, 10, 25, 50, 75, and 100%. The following slides will include examples to better understand each approach. Now, the no KBI. Notice in the table 1 example, we have the user utterance and the system utterance. User says, hello, system, hi, how can I help you? User, I would like to book a reservation at an expensive restaurant in Paris. System replies, sure, I will look one up. And so on and so forth. A simple conversation. This is the most basic example we have in this experiment. In the next table, we are varying the history, which means we look into the previous pair, we take a chunk of it, and then we augment it at the end of the current pair. For example, in pair number 3, we look at pair number 2, we take half of it, which is I would like to book a, and then we augment it here. The relation sets is the addition of previous history. So here we take 50% in this table, and the third table take 100%, which means I look at the second pair, I take the entire pair 1, put it at the end. I look at pair number 3, go back to pair number 2, take all of it in this example and put it back there, and so on and so forth. So we used this new data set for each of these variations, and we ran our experiments. Now, in the second experiment, we are trying to use a knowledge base. So here we have a simple knowledge base: object, predicate, subject. We have objects like expensive, moderate, which are mapping to price. We have Paris, Beirut, which map to location. And we have Italian, French, Lebanese, which map to cuisines. And these are the actual values for these tuples. Now, in this example, we will be looking into each user utterance pair. We'll try to see which words map into an object like expensive, Paris, so on, and then we try to get the value or the subject of that object and augment it at the end. So for example, here I would like to book a reservation at an expensive, so this is one word. We have Lisa, El Sorrento, and Chepipo. These are expensive in Paris. And then we have also Lisa, Chepipo, Sorrentino. So we take all of these, we intersect them, and then we augment them at the end. Third pair is silence for Italian. So we find all the Italian restaurants, which are Sorrentino and Napoli, and we augment them at the end. So this is 0% history. We just go to the database, to the knowledge base. We're intersecting the common subjects, and then we are augmenting at the end. In table number 6, it's the same story, except that I'm taking 50% of the history of the previous pair. For example, in pair number 3, I will look at pair number 2, take half of the words, put them back in. Pair number 4, I look at pair number 3, take half of the words, and put them back in. So, for example, table number 4, I look at Italian would be great. I put the Italian restaurants, El Sorrento and Napoli, and then I take half of the previous pair. And so on and so forth for table number 7. I also will take the entire history of the previous pair. But notice one thing in table 7 is that when I say Italian would be great, imagine I have a knowledge base that has hundreds of Italian restaurants. Then I will have to augment all of these restaurants here in blue, which will make the pair really large. And then I need to look at the previous pair, which is pair number 3, and take all of this pair and augment it at the end. Now imagine I have more than 4 utterances. So if I have 10 utterances, for example, then the last pair will contain so many words. The knowledge base will, the data set will be unbalanced in terms of the number of words in each pair. So to resolve this issue, we will go to the intersecting predicates KPI. So what does this do? Here in this approach, we will keep a separate data structure called a map on the site. We will have the price, location, cuisine as keys, and the values will be updated as we are going through each pair. So, for example, in pair number 1, hello, we don't have any predicate that matches the map. So we go to pair number 2. I would like to book a reservation at an expensive restaurant in Paris. So I know that the price will be expensive and the location is Paris. So I take these two, I find all the restaurants that are both expensive and in Paris and augment them at the end. Perfect. Now in pair number 3, I don't have anything, no predicates, so I keep the data structure the same. Here I also have Italian. So now I update my map with Italian. But instead of fetching all Italian restaurants, I fetch all the restaurants that are expensive, Paris, and Italian. So you can see what we're doing here. We are updating and we are intersecting between the pairs of an entire dialogue together. In pair number 2, we do the same thing. And also, instead of sharing the history of the pair, we only share the history of the restaurants themselves. So in pair number 3, for example, we take 50% of the previous history, but not with the pair, without the actual words, just the restaurant reservation. So Lisa, Chepipo, El Sorrento, we take half, which is Lisa and Chepipo. And so on and so forth for pair number, for table number 10. In table number 3, we take all of these restaurants, so Lisa, Chepipo, El Sorrento, and in pair number 4, the same thing happens again. For the training time, we have conducted 3 approaches, as we said, and in each approach we did 10 history variations, 6 history variations, and for each history variation we did 2 k-fold cross validation methods, which are K10 and K5. So 15 iterations times 6 different history variations times 3 approaches, which brings the total to 118,200 minutes, which is about 80 days. Now, the results, it can be quite obvious here that the intersecting predicates KBI is dominating both graphs. We can see that from the start till the end, the intersecting predicates KBI achieved top results. The all predicates KBI first started below the no KBI, and then it became better, and then it fell back again. And this can be explained because at 0% history, we have some pairs that will contain hundreds of words, and then this means that it will be a less balanced dialogue. On the other hand, when we have 100% history, the dialogue will be overfitted because we have so many words in each pair, and the last pair will contain hundreds and thousands of words. So this is why it will achieve less accuracy than its counterpart in the no KBI approach. And the same thing goes for K5 and K10. But one thing to notice here is that we're achieving the highest results not at 0% nor at 100%. We're actually achieving it at 50%, which is 83.63. So this is something interesting. So when we try different variations, we can see that 50% history is actually better than 100 or 0%. So what to take out from this paper is that using a knowledge base is obviously better than not using one. And when using a knowledge base with history, an amount between 10% and 75% of history yields better results than 0% or 100%. And the better approach when using a knowledge base would be to use a map to store predicates of KB, which is a context, rather than intersect predicates pair by pair. These are the references, and thank you.